Welcome back to World Decoder, where we dissect the most complex military technologies and the physics that make them possible. While Shahed drones are like slow but persistent lawnmowers, the Fattah one represents a completely different entity in the modern sky. This weapon represents the most advanced group on the planet, belonging to the elite class of hypersonic missiles known today. With claims of reaching speeds between Mach 13 and Mach 15, Fattah 1 is not just a fast arrow flying overhead. It represents an extremely difficult physics problem that modern defense systems are currently struggling to solve effectively in real time. To truly understand this threat, we must first define what hypersonic means in the context of advanced military aviation technology. To be called hypersonic, an object must travel faster than 5 times the speed of sound, exceeding Mach 5. At this incredible velocity, the air surrounding the missile is no longer a normal gas, but becomes a fiery plasma. This plasma layer is caused by maximum friction, changing the fundamental aerodynamic environment in which the missile must operate successfully. The numbers are staggering, as Fattah 1 travels at approximately 18,000 kilometers per hour towards its intended destination targets. It can cover a distance of 1,400 kilometers in less than 7 minutes, leaving zero room for error. However, speed brings heat, and the temperature at the tip of the missile can soar to over 2,000 degrees. Without protection, ordinary materials would melt like a piece of butter when cutting through the dense atmosphere at such speeds. The secret of Fattah 1 lies in its special heat-resistant ceramic shell and high-strength carbon alloys designed for extreme conditions. These advanced materials ensure the weapon does not disintegrate, maintaining its structural integrity while piercing through the thick atmosphere. The biggest difference between conventional ballistic missiles and Fattah 1 is not just speed, but the capability of active navigation. Traditional missiles fly in a fixed arc, much like a ball thrown into the air, making their path predictable. Air defense computers can easily calculate the impact point of these traditional weapons to intercept them before they land. However, the Fattah 1 utilizes MAVE technology, equipping its warhead with a secondary engine capable of changing its flight direction. This vector control capability allows the missile to maneuver significantly while it is still inside or outside the atmosphere. Instead of using conventional control fins, which can snap at hypersonic speeds, Fattah 1 uses a different method for steering. It employs gas thrusters to steer the trajectory abruptly, using the force of propulsion to alter its course instantly. This makes defense radars see the target, but they remain unable to predict which direction it will turn next. Modern systems like Patriot or THAAD are designed to confront targets with predictable trajectories that follow standard ballistic rules. When facing Fattah 1, these advanced defense systems encounter 2 major physical barriers that are extremely difficult to overcome today. The first barrier is the plasma wall, a layer of ionized gas that acts as a shield against detection. This shield absorbs and interferes with radar waves, making precise target locking nearly impossible for ground-based defense units. The second barrier is reaction time, which is critically reduced when dealing with an object moving at Mach 15. The time from detection to impact is too short for humans or even older computers to launch an interception. Fattah 1 is not just proof of military potential, but a leap forward in material science and automatic control engineering. Mastering hypersonic velocity and maneuverability within the atmosphere indicates a complete shift in the concept of future offense. This technology forces military strategists to rethink the balance between attack capabilities and the limitations of current defense shields. But we must ask ourselves, is speed truly everything, or are there other secret factors helping these arrows penetrate? Are there hidden elements that allow these weapons to breach every protective fence erected by the world's superpowers? Subscribe now so you do not miss part 3, where we explore the mysterious underground missile cities of the Middle East. Let us look deeper into the engineering marvel that allows such a heavy object to dance through the upper atmosphere. The aerodynamic stability required at these speeds is immense, requiring calculations that push supercomputers to their absolute processing limits. The onboard computers must survive extreme heat while making thousands of trajectory corrections per second to stay on target. Space-based sensors are currently the only reliable way to track the initial launch heat signature of such weapons. However, once the missile begins its glide phase and maneuvers, even satellites struggle to predict the final impact location. The solid fuel engine provides the necessary burst of power to propel the weapon to hypersonic speeds almost instantly. Unlike liquid fuel rockets that take time to prepare, solid fuel allows for rapid deployment and immediate launch capability. This mobility means the launch platform can hide in rugged terrain, shoot, and relocate before the enemy can counterattack. Hypersonic missiles can also deploy decoys or use their speed to overwhelm defense batteries that have limited ammunition supplies. The development of carbon-carbon composites has been a game changer, allowing structures to withstand thermal shock without cracking. Testing these materials requires massive hypersonic wind tunnels that can simulate the extreme environment of Mach 15 flight. Strategically, this weapon alters the deterrence landscape, giving regional powers the ability to strike distant targets with impunity. The arms race never ends, as defense contractors rush to develop lasers and faster interceptors to counter this new threat. Once the booster stage separates, the warhead becomes a small, agile glider that is incredibly difficult to spot visually. It can perform a skip glide maneuver, bouncing off the dense atmosphere layers to extend its range and confuse radars. From the perspective of the missile, the ground moves by at a dizzying pace, requiring autonomous navigation systems to adjust. High-precision inertial measurement units are the brain of the operation, keeping the missile oriented correctly despite chaotic forces. The plasma sheath also creates a communication blackout, meaning the missile must be fully autonomous during the terminal phase. This autonomy means the weapon relies on pre-programmed logic and sensors to find its target without external guidance signals. Economically, the attacker has the advantage, as these missiles are often cheaper than the multi-million-dollar systems used to stop them. Mass production of such weapons could saturate even the most advanced air defense networks through sheer volume of fire. Military experts worldwide are closely monitoring these developments, realizing that the era of hypersonic warfare has officially arrived today. A failed interception attempt results in wasted resources and leaves the target vulnerable to the incoming hypersonic strike payload. The vector nozzle technology is a masterpiece of engineering, handling extreme pressure while providing delicate control over the flight path. Shockwaves created by the missile can be detected, but calculating a firing solution remains the primary challenge for defenders. By flying at lower altitudes than traditional ballistic missiles, Fattah 1 stays below the horizon of long-range radar detection systems. This delayed detection significantly reduces the warning time available to civil defense authorities and military command centers on the ground. When the warning finally comes, there may be only seconds left to react, creating a high-stress scenario for operators. In its final phase, the missile dives vertically, utilizing gravity and its engine to reach maximum kinetic energy impact. The sheer kinetic energy of an object moving at Mach 15 is enough to destroy fortified bunkers without explosives. This makes it an ideal weapon for targeting deep underground facilities that are usually immune to conventional airstrikes. Fattah 1 stands as a symbol of how asymmetric warfare is evolving, relying on technology to level the playing field. As nations observe the capabilities of Fattah 1, the global strategy for air defense is being rewritten from scratch. The challenge for the future is not just building higher walls, but building smarter shields that can adapt instantly. Artificial intelligence will likely play a key role in future defense systems, predicting trajectories faster than any human. The eternal dance between the sword and the shield continues, with hypersonic speed currently leading the deadly waltz. Without the breakthroughs in ceramic and carbon materials, none of these aerodynamic maneuvers would be physically possible to execute. And without the advancements in solid fuel propulsion, the rapid reaction capability of this weapon system would not exist. The sky above us seems peaceful, but it has become a highway for the fastest machines ever built by man. As Fattah 1 disappears into the clouds, it leaves behind questions about the stability of international security and peace. But speed is not the only secret. Where are these weapons stored? How are they kept safe from airstrikes? Beneath the mountains lie entire cities dedicated to the storage and launch of these formidable hypersonic ballistic missiles. In our next episode, we will uncover the architectural marvels of the most mysterious military underground networks in the Middle East. Make sure you are subscribed to World Decoder and have notifications turned on so you do not miss that revelation. From Mach 15 speeds to plasma shields and vector control, we have decoded the physics behind the Fattah 1 mystery. Technology evolves, and we are here to decode every step of that journey for you, one video at a time. Thank you for watching this deep dive analysis. This has been World Decoder. Stay curious, stay informed, and we will see you in the next decoding session.